Good morning. I hope that you are hearing us well. So good morning. Welcome to this first webinar on KWANTEACH, the platform for training and education in quantum technologies. My name is Rabi. I am the founder and CEO of KWANTECH, and I'm very happy to have you here with us today. So I will introduce the participants of today's webinar and their role. So we have from my team of KWANTECH, Zoeb Khan, who is a photonics engineer, graduated from Aix-Marseille University in France, who worked as a sales manager in quantum communication for several years, and who is now at KWANTECH, our sales manager for KWANTEACH. We also have Paul Massiot, also a photonics engineer with a Master 2 degree from Rennes University, and Paul is supporting our customers on KWANTEACH. So during this webinar, Paul and Zoeb will introduce the KWANTEACH platform and perform some live demonstrations during about 20 minutes. We also have the pleasure to have with us Simon BERNON. So Simon graduated from École Polytechnique, followed by Institut d'Optique. He did his PhD in the Charles Fabry laboratory in the atom optics group of Nobel laureate Alain Aspect. As a postdoc, he studied cold atom and superconductor science at the University of Tübingen in Germany, and then at CEA in France. Simon is now leading a research team on cold atom hybrid quantum systems, and he has been teaching for the last 12 years at Institut d'Optique Graduate School and the University of Bordeaux as an associate professor in quantum physics. Simon is here, and we are really glad to have you, Simon, to share your experience with KWANTEACH that you had with your university students. So during this webinar, please feel free to ask questions. There is a dedicated tab in the chat box. We will collect your questions and we will have a dedicated session to answer your questions at the end for the remaining 20 minutes of this 1 hour webinar. So with this, I will switch to a first introduction about the company and then leave the floor after to Paul and Zoeb. So shortly, we are the company KWANTECH, a quantum sensing deep tech startup that I founded after nearly 15 years of experience in teaching and research in quantum technologies. We develop and commercialize metrology solutions based on diamond quantum sensors with a team of 24 people. Our headquarters are located in the west of France. This is where we have developed the KWANTEACH platform and develop our other metrology solutions. Why are we here today? So as most of you are aware of, training in quantum technologies is today a global need. Several professors, university professors, college professors, high education professors have outlined the importance of practical training to grasp the key concepts of quantum technologies beyond the theory courses. And what we will show you today is how this challenge and this need can be addressed with the platform KWANTEACH. In the next 20 minutes that we have, from my side, Paul and Zoeb, we will first briefly describe the basic physics of the NV diamond, and then present you in more detail the KWANTEACH platform by performing live demonstrations. At a glance, in all the products that we develop at KWANTECH lies a core technology, which is called NV diamond, in NV centers in diamond, which comes from about 25 years of academic research internationally. The NV center is a particular defect in diamond that is shown here. So diamond is a well-organized structure of carbon atoms. These are the balls that you see here. And we can replace artificially one carbon atom by a nitrogen and leave a hole or a vacancy aside. This so-called NV defect has exceptional optical and quantum properties that allows to perform various measurements, precision measurements, at room temperature. The diamond that you can see here, it's a piece of about 1 cubic millimeter, is simply irradiated by a green laser and then emits red light that is collected to perform the measurements and read the state of the qubit. In more detail, this is here on the right, what is the fundamental state of the NV center. You have a so-called bright state corresponding to a particular projection of the spin state of the electrons, and a dark state, which emits less red light. The remarkable property of the NV center is that under the illumination of green light, the spins are polarized in the ms equals 0 state. By shining a microwave signal that is resonant with the transition from m equals 0 to m equals plus minus 1, we can transition the electrons from the m equals 0 state to the m equals plus minus 1 state. By doing so, and by changing the frequency of this microwave, we can observe a resonance signal which is detected optically. This is the plot that you see on the bottom right, and that Paul and Zoeb will illustrate to you practically in a minute. This phenomenon is called the optical detection of the magnetic resonance. In the presence now of a magnetic field, we do not have anymore one resonance, but two resonances. One which corresponds to the transition between the m equals 0 and minus 1 states, corresponding to a particular projection of the magnetic field onto the NV axis, and another resonance corresponding to the transition from m equals 0 to the m equals plus 1 state. The difference in frequency between the two resonances is given by the Zeeman effect, which splits the line according to the magnetic field. So this is a key concept for performing magnetic fields and at one of the building blocks of KWANTEACH. So with this, I will now leave the floor to my colleagues, Zoeb and Paul, who will present you in more detail the platform.
Thank you very much, Remy. So my name is Zoeb Khan. I'm the sales manager for Kwan-tek.
And my name is Paul Massiot. I am the photonic engineer in charge of KWANTEACH.
So thank you, Remy, for this nice introduction and also the explanation and theoretical reminders. So as you can see on the picture, this is our full platform, the KWANTEACH. As you can see, is a fully open platform, modular platform composed of several modules. So you have, first of all the optics, the whole hardware. So this is nice and great for students to learn and teach them how to align a laser, what are the key components when you're doing alignment, such as noise analysis, precise positioning of mirrors and irises. You have also on the picture the two units that we have specifically designed for controlling every single component of our platform. And we also provide the full software being able to control and manage the whole experiment and all the experiments you can do. So you can see that this is a fully open platform. You don't need any vacuum or cryogenics. This is working at room temperature, and the fact that it's open really give you a total freedom and customization possible for your specific experiment. So, of course, you are not alone with this. We provide a full technical manual explaining the theory, also how to implement every single experiment with the platform, what parameters to use, how to make the alignment, and also showing the expected results. So in this manual, we have gathered up to 15 lessons, but it's still evolving, and according to your needs, we can also adjust it if you have specific experiment you would like to add. So this is really to support you and help you to gain some time when you are preparing your lab courses. And finally, before going directly and showing you the platform, just a piece of information, the KWANTEACH is actually divided in two modules. So you have the base module where you can measure the ODMR, the detection of the magnetic resonance. You can measure the Zeeman effect, like you have seen before. You can also see the hyperfine structures. So this is really interesting for students to go that far, and you have a precise measurements of the magnetic field. So this is the base module where we will be using the continuous wave laser. However, if you would like to go a little further in the physics, and if you would like to see how this quantum system based on NV is evolving in time, you can add the extension, the pulse extension, and in this pulse extension, we will be generating pulses of lasers, but also pulses of microwave, and we will be able to generate sequences so you can measure the T1, for example, the T2, T2 star, and the very famous Rabi oscillation that we will show you right after. So enough with the presentation theoretically. I will let the stage to Paul, who will show you the platform in live.
Thank you, Joël. So what you can see here is the base module and the pulse module on this breadboard. So let's focus on the base module. So it consists of a green laser source that is located here. The beam is reflected on these two mirrors, this one and this one, and then goes in a direct mirror, which is mounted on the optical cage system. And then the beam is focused into the NV center diamond that is placed in the middle of a 3-axis Helmholtz coil. So if we look what is going on inside the coil, if I had a red filter in front of the camera, you can see the red spot on the middle of the camera, which is the NV center diamond that emits fluorescence. So you can see that on the right, the NV center diamond is glued to a microwave antenna, which is the red PCB on the right. So next, to detect the photoluminescence, the photoluminescence go back through the direct mirror and goes into a photodetector, which is located here. So what is very great is that students can directly see the fluorescence by eyes. So it's very great. And now we are going to present to you the base module software.
Thank you very much, Paul, for this presentation. So as you can see, the base module is pretty simple. However, it's still really powerful because you really have huge possibilities with the platform. So once we have done everything with the hardware, let's switch to the software part. So I'm going to show you the software part. So for example, let's switch to this before. So we have 4 different tabs in the software of the KWANTEACH base. One for the acquisition parameters. You have one timing acquisition that can be interesting for students if they would like to make some optimization of the signal, for example. You can also have a spectral analysis of your signal if you want to see the noise analysis that is also very interesting, and you have one RF tone. On the ODMR acquisition, you have the first box where you can choose the settings of your acquisition because we are making basically a frequency span from low frequency to a high frequency. You can add the number of averages, change the number of points, and change also the microwave power so you can know what would be the impact of having a low power or high power. So I'm going to start really easy with ODMR, and Paul will start with an ODMR without any field, so with the field of 0. And we have chosen the right range from 2.76, for example, to 2.98 gigahertz. You just have to click start. We will just add, just to show you this feature, just add an average of 2. You just have to click start, and the measure is going on. So we are just clicking on the auto scale button so you can see directly. Good. As you can see here, we will be having an average that is getting rid of this this small defect. So as you can see, you have the typical ODMR curve. At 2.87, you have a drop of fluorescence due to the magnetic resonance. So that's the very first ODMR. We are able to say, as you can see, it's really quick and short. So now let's see what happens if I apply a magnetic field. So I'm choosing, let's say, a magnetic field of 1.9 millitesla in norm. We have set the parameters on the theta phi angle. So you have two options here. You can either use the spherical coordinates, or you can also use the Cartesian coordinate in XYZ. Once the field is chosen, you just have to click on field on. Once the field is on, you can just click on start again. So we are keeping the same window with now for measuring the magnetic field. And here you have it. So you have, and now the question is what do you have here? You have an ODMR showing the 8 different lines in the structure. So quick reminder: so the NV can be placed everywhere in the diamond, and the NV can be located only in the diagonals on the diamond lattice. So you have 4 different orientation. So it means that you have 4 different pairs of NV families in the diamond. So you can count 1, 2, 3, 4 for the -1, for example, state, and 1, 2, 3, 4 for the +1 state. So it made 8 different lines. Another very great point would be to see that you are able to see the hyperfine structures. So this is interesting for your students, so to see that you can go that far with only the base module. So right now we have a magnetic field. Let's focus on these, for example, this family around 2.87. So you have one family here of the NV, the other one here. So you can note approximately the frequency, 2.86. You can, with the cursor, you can see this one is around 2.87 gigahertz. And now I would like to highlight the Zeeman effect and what happened if we increase the magnetic field. So we are choosing the same coordinate just with a higher magnetic field, a 3.4 millitesla, and you just have to click on again and just start. So we are starting the measurement. Everything is the same. It's just that the frequency is just that the norm of the magnetic field is higher. And if we are looking carefully, you are able to see that around 2.87 gigahertz, the two families, the 2 lines we have chosen, they are more splitted than before, 2.86, and now you have 2.88. So you had a bigger splitting because we have increased the magnetic field. And you are also able to see that this extreme line is way far than the other one. So that's a very good thing. So you have 3 lines here also that are basically far from the 2.87. So that's to highlight how you can use the KWANTEACH to make the Zeeman effect measurement. So let's switch to the pulse module now. We would like to show you how to switch from the base module to the pulse module really easily and quickly. So I'm gonna, Paul will explain you every component of the pulse module. So let's switch to this.
So to switch from the base module to the pulse module, we simply use flip mirrors. So the first one is located just here, and it allows to reflect the beam into acousto-optic modulator that is located here, which is aligned in double pass configuration. So the beam goes here and is reflected like this. Then the other flip mirror allows to align the optical path as the same as the base module. So the green goes like this. He excited the NV diamond, and then the fluorescence arrived here. And the third flip mirror allow to detect the photoluminescence through an optical fiber, which is connected to a multipixel photocounter that is located here. So now the web will present you the Pulse software.
Thank you very much, Paul, for this explanation. So since we are switching to the Pulse software, we are now able to have a different kind of measurement. So you have the T1 measurement that is possible. You have also the Rabi oscillations and the hand echo and the Ramsey fringes. And now that we are able to generate pulses of lasers, but also generating pulses of microwave, we are able to create sequences. And for each measurement, you are able to see, you are able to set a sequence. So as you can see, Paul is actually showing you the sequence. So if we zoom in, you have a sequence on, you have a sequence that you create directly with the software. You can generate, and you can see you are generating pulses, then you wait a certain amount of time. This is for T1. And you have several parameters you can play on: the maximum dark time, the minimum dark time, the pulse width. Basically, we give a total freedom on how to generate a sequence and how you can set the sequence for your measurement. So Paul is now adjusting in the hardware to have the best measurement possible. So we are using also the sequence. If we switch, for example, so you have also the Rabi oscillations and the Ramsey fringes, the hand echo, that have the same, more or less, sequencer with different parameters. So we will be, we are adjusting the pulses to have the best signal possible and being able to measure, for example, Rabi oscillations. And you, as I said, once you have set every single parameters in this sequencer, then you are able to see it. And you have also a sequence length that will give you an idea on how long would be one or the other measurement. So now Paul has finished the adjustment, and then he can enter inside the base module. He will be choosing one of the hyperfine lines, for example. So he's zooming to make an Rabi oscillation at this specific frequency. As you can see, he's choosing 2.79112. This would be the frequency he will be choosing in the Rabi sequencer. And you can also choose the power, for example. You can have different parameters to play on. Paul is adjusting everything to see that. As a reminder, for those who don't know, the Rabi oscillation gave information on how the states of this quantum system are populated. And now Paul is showing, so you have in green, you have the laser light, then you have in gray, you have the microwave power, the microwave duration. You just have to click on set sequence and switch to the pulse and launch the measurement. So now we will be launching the measurement of the Rabi oscillations. And you can see for every pulse, you are able to see on the left side the pulse, and on the right side, you are able to see that it starts drumming itself, the Rabi oscillation. So we just have to wait a certain amount of time. You can in live play with the parameters to be able to adjust as you wish your measurement. So we are seeing right now that the Paul is actually adjusting the pulse on the left side and trying to have the best Rabi oscillation possible on the right side and live. So Usually the measurement takes less than 1 or 2 minutes once you have everything aligned. So now in live, I've shown you how easy it is to go from base module to the pulse module and how you can adjust it quickly. So now you are able to see the shape, the typical shape of Rabi oscillation. That you can see that at the beginning you have the maximum of I would say electrons in the ms equals 0 states, and after a certain amount of time, that is called the pi pulse, you have the total inversion of population. This is around here, so it means that all of your electrons have done this transition, and in the middle of these two, so the pi over 2 pulse, you have a linear combination of the two states. So really giving the basic of quantum physics for your students, and it's done really, really quickly, easily. We have done it live, so you can see how easy it is and how fast it is to see a Rabi oscillation. For the T1 and the Rabi oscillation, we have we have added a fit feature, so you can see how far it is. And for both software, for the base software and the pulse software, we provide, we give access to the raw data if you would like to if you would like to make some post-processing afterwards. So you can see the pi pulse here, that correspond in nanoseconds to this, as I said, point, which is 113 nanoseconds. If you divide by 2, you have the time needed to have a linear combination on this here. And if you let the system make the measurement, though, your R factor would be even higher. So I think I've covered pretty much everything in the base and pulse module. So of course we have a lot of possibilities that I'm not going to show you, but I think the best is to let the stage again to Simon and Remy. So thank you very much for your attention. If you have any questions, please let us know.
Thank you very much.
Thank you very much, Paul and Zoeb. So now I will have the pleasure to have Simon with us, who will share his experience. And in the last part, we will be able to come back to some of the questions that were asked in the presentation. So the floor is yours, Simon.
Thank you, Remy. So hello, everyone. So as said by Remy, I am an assistant professor at the Institut d'Optique in Bordeaux, and also teaching at the University of Bordeaux. In Bordeaux, I am responsible of the experimental practice, the organization of all experimental practice for the Institut d'Optique, and I'm also responsible for teaching in quantum physics lectures. So that's why I'm here to talk about experimental practice in quantum technologies that we carry in Institut d'Optique and in collaboration with the University of Bordeaux. So if I say Bordeaux, you may think first of seasides or the nice wineries of Saint-Émilion, but that will not be the focus of my talk. I will go downtown in Bordeaux in the university. So the university is situated in the heart of Bordeaux. It's actually about 60,000 students who are in the university. But in the university, I will actually more focus on the students that are in Master 1 and Master 2 level, so at 4th and 5th years in university, because this is the students for which we teach quantum technology in experimental practice. So actually, within the earth of the university, we have a very nice building, which was granted by the states, which is hosting the Institut d'Optique. So Institut d'Optique is an engineering school, so it's a bit specific of the French system. This is teachings to students at the Master 1 and Master 2 level. So the building is actually hosting the Institut d'Optique, but it's also hosting a laboratory and some innovation center. Right. So within this building, there is quantum physics research, and we need to train the students for this research. and to spread our students over different institutes. So let me discuss what kind of system we are talking about. So let's illustrate a quantum system by qubits, so state 0, state 1, and any superposition in between. If we want a good quantum system, this system is embedded in an environment. And this system should not decohere, which means that it should be very little coupled to the environment, if possible, not coupled to the environment, so that we can really conserve the coherence of the quantum system. Nevertheless, we need to manipulate this system. So we need to have an access to the quantum system by the user, which is part of the environment. So there is kind of a contradiction here, because environment should not be coupled to the quantum system, but the user should be coupled to the quantum system. And more important, the quantum systems should be coupled in between each other. Okay, this is interconnections between quantum systems, so that we can make, for example, gates and perform operations with this quantum system. So this is kind of sketch of the ideal quantum systems. In practice, this is usually realized either with system in the vacuum, like atoms, molecules. This is the field of AMO physics, or within solids, where we can embed the quantum system, like molecules, quantum dots, or the NV centers that were presented just before. And that will be the focus in a few slides. All right, so these kind of systems, what are they good for? So in terms of research, there is 4 trends which have been identified. There is computing, where we use the qubits as classical bits to perform operation, but because they are qubits, then the operation can be a lot faster. So this is, for example, performed on superconducting circuits, like the Sycamore processor. But it can also be used to make precision measurement. This is the field of metrology, like measuring fundamental constants, but also measuring some quantity of the environments that you want to measure, like gravity, rotations, magnetic fields. And this uses essentially the quantization of the quantum physics. This quantization leads to the fact that the electric field is actually carried by photons, and which opens on the field of quantum communication, which allows to make secured transmissions of information between 2 persons. And this is infinitely secured because this is secured by the laws of physics. And the last is quantum simulations, where we use the system to predict the properties of materials. So these are the fields of research, but if we want these fields to expand, we need students to work on these topics, and we need to train the students. So we have some pedagogical objectives so that the students can work in these different fields. So, for example, for quantum computing, we need the students to understand and be able to manipulate the coherence of states of the qubits. When it comes to quantum metrology, we need the students to understand the Hamiltonians and how does the environment plays a role in the evolution of the quantum system, so in the Hamiltonian. And this allows to then measure the role of the environments, and eventually measure precisely some quantities of the environment, like, for example, magnetic fields. When it comes to quantum communication, as I said, this is usually carried by single photons, and single photons have some specific properties which needs to be characterized, and this is typical topics that we can train the students on. All right. So for training, we need platforms. So there is the Kwan-tek, which I will detail in a few slides. How do we use it? And we have also developed an homemade cold atom platform. So you see this image where you see the 2 coils, and in between a cell. This cell is actually under ultra vacuum. And within the cells, we have 6 beams that converge all together at the same point, which allows to cool down a cloud of atoms. So this is performed, and this is the one I will detail now. This is performed in Bordeaux. So here you see the same picture where you see the overall system of the cold atom system. So you see again the coils with the UHV cell in between. You see the trace of the laser the laser trajectories that are converging into this cell. So you see that it's a rather complex system. It's actually having many different blocks, which allows us to have the students work on these different parts. So you see that there are some fibers on these systems, which allows for the students to work with, to manipulate fibers and telecom laser systems. We have nonlinear optic systems, which allow to convert from telecom wavelengths to infrared, near-infrared wavelengths. So there is frequency doubling. There is a rubidium cell where we do atomic spectroscopy. There is obviously a need to detect the light. So there is photo detection, which leads to analog digital signal processing. You see on the top an acousto-optic modulator, which train the students on an optoelectronic device. And obviously there is 6 beams that needs to be all together in the same place at the same time. So this is quite some alignment protocols, which are quite difficult. So altogether, we need the students to be able to manipulate all these topics so that in the end, they reach a quantum system in the cell. So this is a lot of engineering, and this actually takes 6 weeks for the students to master all these parts all together. And in the end, we train up to 10 students per year on this type of platform, because this is a lot of technological investments, so that in the end, we reach cold atoms in the cell. So this is so this is a lot of learnings for the students, but only for 10 students. Okay, so what is the system that we have in this cell? So this is alkaline atoms. So here it's a complex structure of an alkaline atoms. Actually, we can see this as a lot simpler system because, as you see, there is a single electron on the outer shell. So it's actually like an hydrogen atom where there is only one proton and one electron. The core electron plus the nucleus forms this macro proton. It interacts with the electrons with Coulomb interactions. But there is more in this system because the electron has a spin, it's rotating around the nucleus, so there is a momentum which leads to a magnetic moment, and the proton has also a spin, which leads to a rather complex structure, but which is very well understood, where there is some infrared transition and some microwave transitions. This actually reminds, and this is my connection to the NV centers, because you see that we have seen in the presentation of Remy and Zoyed that there was electric dipole couplings, like couplings to the light fields, which is the same that we had with atoms, and also coupling with microwave fields, so magnetic microwave couplings to spins, which was in between the fundamental state. So in the case of the NV centers, this is at 2.87 gigahertz, but whatever the frequencies, this is a magnetic coupling. So we see that with actually these NV centers, we have access to the same type of physics than we have with cold atoms or with the purest quantum system, which are atoms. Okay, but these NV centers, they are embedded into the crystal, and that makes that this is extremely simple to make the experiments. We have seen this platform that was presented by Zoyeb and Paul. And as you have seen, I mean, in the end, this is essentially one laser, a few mirrors, one splitter, and a crystal. And with this, we have access to many topics, which makes that this is extremely simple for the students to have access to the quantum physics without having to deal with the engineering of the system. All right. So let me detail a bit what are the connections with our lectures. So we have seen the KWANTEACH base. The KWANTEACH base essentially is looking at the Hamiltonian and trying to understand the role of the different terms of the Hamiltonian. So we see in this Hamiltonian, there is the first term, which is the hyperfine structure. So this is the spin-spin interaction, which leads to the 2.87 gigahertz splitting. There is also a strain, which is very interesting because actually it adds some complexity into the diagonalization. And this is very interesting for the students to understand the connection between the hyperfine structure and the strain. And then there is the Zeeman effect, which is how the system is affected by the environment. All right, so the connections are quite clear with the lectures. This is clearly connected to quantum mechanics lectures and to atomic physics lectures, as I just showed before, that the atoms, real atoms and NV centers actually share many similarities. It allows to work on quantization axis properties and the role with respect to crystallographic axis, on the diagonalization of the system to find the eigenstates. And when it comes to applying a magnetic field, then it becomes a magnetic field sensor. And we can observe some quantum behavior like microwave transition broadening when we increase the microwave power. All right, so that was the KWANTEACH base, which is essentially, for us, taught at the Master 1 level. The pulse is targeting a different level of understanding. First, there is some more technical instruments, which is the acousto-optic modulator, which is used in double pass, which is a quite conventional architecture. But this is well used in research lab and is connected to optoelectronic lectures. And with this, this allows to pulse the lights. As we can pulse the microwave, then we can really do some coherent manipulation of matter. The states can be initialized. Then we can measure coherence time, Rabi oscillations. This was just shown before, or going towards interferometry, carrying Ramsey interferometry, and eventually some spin echo sequence. So this is in clear connection with Master 2 level topics, which is light manipulation of matter or quantum optics lectures. And the grail with this platform would actually to reach even single NV manipulation, because then we could go towards single photon source and their characterization. All right, so you see that it actually covers quite some topics and close connection with the lectures. All right, so how does, what is the population on which we have tested the system? So the system is there and running for 2 years. The base module has been running for 2 years, and the pulse module has been running only over the last year. So at the Master 1 level in IOGS, we have about 60 students in Bordeaux, and they have a background in quantum mechanics and in atom physics. The students have worked in the system as a team of 3 students over 4 hours. And in the Master 2, this is rather similar. We have a bit less students, about 15 students, and they have background in light manipulation of matter, quantum optics. And they also worked as a team of 3 students over 4 hours on the system. There was some slight difference for the population of the University of Bordeaux, so the master students. there were approximately same number of students, 40 students from the Master 1 level, 15 students at the Master 2 level. And the main difference is that actually they worked for twice more time on the platform. And it actually made quite a difference because over only 4 hours, our students are working on these topics like quantization, initialization, coherence time, Ramsey interferometry, but they are not really taking time to align the system. If they start to align, usually they disalign because they are students, and then it takes quite some time to realign. So actually, because the system is rather robust, then they can really spend their time on the quantum physics over 4 hours. When they have twice more time, then they can play slightly more with the system and see what is the sensitivity of the system to alignment and disalignment in terms of signal to noise. All right, so this is the population which has been working on the system, and maybe I can comment where those the students are ending. So there is a connection with the research that we do in the same institute. So here is presentation of the group of Brian Lunis, which is doing nanophotonics. So they have different topics, among which they are, for example, working on molecules and looking at the emission of molecules. So this is quite similar to the emission of NV centers. This is a quantum system with eigenstates of energy where they can emit light. And an example of connection. So here you see an example where you have two molecules, and these two molecules can actually exchange energy by photons. So this couples the two molecules, and this team could observe superradiance and subradiance of the coupled systems. So this is in close connection with the NV centers, which is emitting light and which could be coupled in between each other. So the physics of the emission is really similar. So now another example, which is close connection from my research. I'm part of the Cold Atom in Bordeaux team, where we have essentially two topics: atom interferometry and hybrid quantum systems, which is more in the field of quantum simulation. So if I focus on the atom interferometry part, so in atom interferometry, we need to manipulate the quantum systems. So here is a design representation of an experiment where you see that we have the 6 beam that cross, it creates the cold atoms. Then we have the blue beam that manipulates the states. So this is the initialization of the states. Then you have the 3 vertical beams that manipulates the wave function, that opens the wave function to create an interferometer, and then the detection in the end with the bright spots. All of these are keywords that I mentioned just before on the NV centers: initialization, state manipulation, interferometry. And these are clearly in close connections with the topics that the students have seen in the experimental practice. All right, so in terms of direction, this kind of physics is performing atom interferometry. On Earth, the atoms are falling, except if we follow the trajectory with the atoms. So there are experiments which are performed in this zero-G plane, which is actually following the trajectory of the free fall. And this allows to test, for example, in terms of physics, the weak equivalence principle. So this is making sure that two mass of different types fall under the same gravity field, same way and same gravity field. And this is also actually leading to some industrial developments which are carried by the Excel quantum physics company. All right, so this is about the end of my presentation. So I presented two teams where obviously the students can do research, but there is many other teams in France or in the international place where our students have been ending over the last 2 years. And this is just a few examples that I could gather like just in a few minutes. All right. So for me, this is about the end, and I thank you for your attention.
Thank you very much, Simon, for sharing your insights. We have some time to come back to questions which were asked in the chat. So there is a question from Nicolas Burger for you, Simon, which is how much engineering effort it was for your team to put in place the cold atom experimental platform that you presented.
Mm-hmm. Right. Actually, this was quite some effort, mostly in terms of organization, I should say, because this has been made bit by bit in terms of engineering over the past 10 years, I should say. This was actually not much made by the research team, rather than by the students. So the students have worked in projects over each bit of each part of this engineering. And that's why it's actually took like many years of development to reach these cold atom systems in the lab. It's extremely good for the students because they learn a lot of engineering skills on all the topics, and they see all the different parts that can be problematic, and we have many. I mean, this year the students have been running the experiment, and there is many parts that stops working for some time, and they have to repair, and so that in the end they can reach quantum gas. But really, the difference with the KWANTEACH is this engineering part. I mean, the engineering part is kind of hidden into the KWANTEACH, so that we can really access to the quantum physics.
Okay. Thank you, Simon. There was another question about the use of the teaching manual. Did you use it for the preparation of your course with the students, or did you adapt it for maybe other experiments?
So yes, we did use it a lot. The manual is actually well done. So the physics of NV centers is now well known in the literature, but the manual is actually a good summary of the type of physics that is done in the experiment. There is, good pictures that we can take for the manuals that we give to the students. We have a bit adapted, so there are many experiments which are proposed in the KWANTEACH, and we have made some focus on some experiments. We have chosen what we wanted to teach for pedagogical reasons. So we have a bit adapted the manual. So we got granted the access to the manual, so we used it.
Thank you, Simon. I will come back to another question which was asked, and I see that others are coming in the chat. So Vinod asked several questions, so I come back to the first one you asked, Vinod, maybe for Zoeb. One was about the power of the laser that is used, another from Vinod about the magnetic field that you apply, and there is one about the price of the solution. So I will leave you, Zoeb, answer these three.
Yeah, thank you very much, Remy, and thank you, Vinod, for your questions. So about the number of experiments that you can do, Remy has listed the whole and exhaustive list in the chat. So as you can see, we have, with the base module, we have 7 different experiments, and we have in the chat, you can see the 8 left for the pulse module. So if I take back your question about the maximum magnetic field, Remy has answered also. Depending on which direction you would like to apply your magnetic field, the value will be different. So it's usually between 3 and 4 millitesla on X and Y, for example, direction. It's a little less. but if you look at the whole range, it's yes, for 4 millitesla. And you had a question about the pricing. So the pricing will actually depend on the options you choose. If you would like to go only with the base module, or you would like the full setup, and this will actually depend on the pricing. So the best way is to contact me afterwards. So you have the address, sales at Kwan-tek, and I can take the lead on that question with you.
There is a question from Didier, and the point is about the number of students that are operating the KWANTEACH platform at the same time. So I don't know if maybe you can answer again, Simon, about how many students you have.
Right. So at once around the platform. So we made the platform so that students can turn around. Okay, so the platform is accessible over 3 sides, and then there is computer on the other side plus electronics. So essentially, the students can turn around. If the students are really working on the experiments, we made teams of 2, 3 students with no big difficulties. When it's only to show the platforms, when this is the more a teacher which is showing the platform, then we can have up to 5 to 10 students to which you show the experiments. But if they work on the experiments, 2 to 3 students at once. Then the students are working for 4 hours, 2 times a week, over a few weeks. In the end, this is a few tens of students, up to, let's say, in between 50 and 100 students who are able to see the platforms over 1 year.
Okay. Thank you, Simon. So we are coming to the end of this webinar. We had another question, last one maybe from Charles-Antoine, who shared his experience as well. And while, Charles, you were asking if we have ambition to provide material to reach younger students below the early master or end of bachelor level. For example, going to high school. So we have been asked to develop such products. For now, our aim at Kwan-tek is really to have the KWANTEACH deployed over more and more universities. But indeed, we have even been involved in some projects to go at lower curricula. So our product in that direction is not ready yet. And we are basically in the stage where we want to collect the needs before engaging in the development of a new product. So as you said, and you illustrated, Simon, it's a big engineering effort to come up in the end with a product that is robust and can be operated for thousands of hours by the students. And before engaging in a new challenge like that, we really want to collect the needs. So thank you, Charles, for sharing your insight on that. Not surprised. And with this, I think I will thank every participant to this webinar. So thank you to the people interested to join. This webinar was recorded, so we will be able to share it with you so that you can share it also with your colleagues. My colleagues, Zoeb and Paul, are of course here to answer your questions if you have more precise questions on the product and its functionalities. And again, Simon, I thank you very much for being with us today. And it was great to have your insights.
My pleasure.
Thank you very much.
Thank you very much.
Thank you very much to everyone.